Good morning, students. Today we are going to read the magnetic effect of a current in the subject of physics O level. So concentrate yourself. Here we are going to start. The first thing for today's lecture is magnetic fields from coils. A current produces a stronger magnetic field if the wire is it flows through is wound into a coil. So the thing is, if we round the coil into wounds, the magnetic field will be more stronger. The diagram below shows the magnetic field patterns produced by two current carrying coils. This is the one pattern, this is the second pattern. One is just a single turn of the wire. So here you can see this is just a single turn of the wire. The other is a long coil with many turns. So here you can see a long coil is called a solenoid. So this kind of the coil, when it is having many turns, is called a solenoid. The magnetic field produced by a current carrying coil has these features. So here are the features of the magnetic field produced by a current carrying coil. Here we are going. So number one, the field is similar to that from a bar magnet. So this is first point to be needed. The field will be similar to that of the bar magnet, and there are magnetic poles at the ends of the coil, and here you can see the poles are there at the end of the coil. Here is north, here is south pole, here is north, here is south pole. Increasing the current, increasing the strength of the field. So more the current, more will be the strength of the field, and less the current, less will be the strength of the field. Increasing the number of the turns on the coil increases the strength of the coil, field. So here is another very important point to be noted, that number of turns will be increased. As the number of the turns will be increased, the field strength will also be increased. As the number of the turns will be lesser, the field strength will also be lesser. The next point is, under identical conditions, an electromagnet with an iron core is a stronger magnet than an electromagnet with a steel core and will pick up a larger mass of the magnetic material. So the point to be noted is that iron core is behaving like a strong magnet and steel core will behave like a weak magnet. When the current is switched off, quite a lot of the materials remains adhering to the electromagnet with the steel core, but none remains on the electromagnet with the iron core. So this is another very important point to be noted. Although the iron core behave like a strong magnet, but when the current is switched off, its electromagnetism will be finished. And although the steel core is behaving like a weak magnet, but when the current is switched off, some of the electromagnetism will still be there in the steel core. A coil without a core only picks up a small amount of the magnetic material. So this is another very important point to be noted, that if there is no core in the coil, so it will pick up only a small amount of the magnetic material. Inserting cores made of the materials such as the copper, brass, aluminium, wood, etc. does not increase the mass of the magnetic material picked up. This indicates that these substances do not increase the magnetic field and are useless as cores for the electromagnet. So these are useless as the cores because they does not increase the magnetic material to be picked up. The strength of the magnetic field produced in the solenoid can be increased by. So solenoid is a coil which is having many turns. So the strength of the magnetic field produced in a solenoid can be increased by, number one, increasing the size of the current. So this is the first point to be noted. More the current, more will be the strength of the magnetic field. Less the current, less will be the strength of the magnetic field. Increasing the number of the turns per unit length of the solenoid. So if you increase the number of the turns, more will be the strength of the magnetic field. If you make less the turns of the solenoid, less will be the strength of the magnetic field. Next point is placing a soft iron core inside the soft iron core concentrates the magnetic field lines, thereby increasing the magnetic field strength. So this is another very important point. If you place a soft iron core inside the solenoid, that will increase the strength of the magnetic field, because the function of the soft iron core is it concentrates the magnetic field lines. So as the magnetic field lines will be concentrated, the strength of the magnetic field will be increased. Next point is bringing the poles together. So if you bring the poles, that is north and south poles, together closer, so the strength of the magnetic field will be increased. And if you make far away, if you make more distance between the poles, the strength of the magnetic field will be less. So here is a figure. You can see many turns of the wire, so it will increase the strength of the magnetic field. And here is soft iron, a soft iron core placed inside the solenoid, so that will increase the magnetic strength of the magnetic field. A two-pole electromagnet figure above is more efficient than a single pole, because when the magnetic material is attached, the lines of the force follow a closed path as shown by the dotted lines. So this is another very important point to be noted, that two-pole electromagnet is more efficient than a single pole electromagnet. Here is another very important point to be noted. Some alloys, for example stelloy, are more suitable than soft iron as an electromagnet's core. These are used in the electromagnets, generators, motors, transformers, etc. So this is very important point, which normally comes in the paper number 1 and in paper number 2 as well. Some alloys, for example stelloys, are more suitable than soft iron as a electromagnet core. Plotting the magnetic field due to the solenoid. Coil a length of the insulated thick copper wire through a horizontal sheet of the cardboard or perspex as shown in figure A. So here you can see, turn the solenoid. Connect the ends of the coil to a DC current. Here you can see the coils are connected to the DC current. Supply through a rheostat and ammeter. Switch on the supply and use plotting compasses to plot the magnetic field. Check that reversing the direction of the current reverse the direction of the field. Here you can see, if we reverse the direction of the current, the direction of the field will also be reversed. The field is shown in the figure B. So here you can see, this is the direction of the current, this is the direction of the field, and when the direction was okay. Here is another point to be noted. The lines of the force inside the coil are parallel straight lines. Here you can see the lines of the force inside the coil are parallel straight lines. Outside the coil, the field is similar to that of the bar magnet. So outside the outside the coil, the field is similar to the bar magnet. As you can see, the lines of the force obey the corkscrew rule. Magnetic field due to the currents in the solenoid. So this is another very important point. So concentrate. When the current carrying straight wire is wound into a coil, the current is seen flowing upward and then downward. We can see two magnetic field with two opposite field directions by applying right hand grip rule. The side where the current flows upward produces a magnetic field with an anti-clockwise direction. So these 2 points are very important to be noted. So the side where the current flows upward produces a magnetic field with an anti-clockwise direction, and when the current flows downwards, it produces a magnetic field with a clockwise direction. So here you can see, if the direction of the current is upward, the direction of the magnetic field is anti-clockwise, and as the direction of the current is downward, the direction of the field is clockwise. So these two are very important points to be noted. If we increase the number of the turns on the coil, a solenoid is formed. So here you can see the number of the turns are increased. So now the coil is called solenoid. The magnetic field produced by the current in a solenoid is shown below. The magnetic field pattern is similar to that of the bar magnet. One end of the solenoid acts like a north pole and the other end is a south pole. So here you can see north and here is you can see the south pole. To know, so this is another very important point as far as your paper number 1 and 2 is concerned. To know which end is the north pole or south pole, or when viewed from any one end of the solenoid. So look now, here are two very important points to be noted. If the current flows in a clockwise direction, so look now, from here I'm seeing that the current is flowing in the clockwise direction. This end is the induced pole. So you can see from this end the current is flowing in the clockwise direction. So this end will be induced south pole. And if the current flows in anti-clockwise direction, this end is induced north pole. So here, if I see this figure, the current is flowing in the anti-clockwise direction, so this end will be induced north pole. So these two are very important points. So this is these points are to be noted. Rule for the poles. So here you can see, here you are going to read a rule that is called right hand rule. To work out which way around the poles are, you can use another right hand grip rule. Imagine gripping the coil with your right hand so that your fingers points in the conventional current direction. So if we hold the wire in such a way that our fingers round in the direction of the conventional current, your thumb then points towards the north pole. So the thumbs will point towards the north pole. So this is called right hand rule. Listen again. If we hold, so look now, if we hold the wire in such a way that our fingers round in the direction of the conventional current, then the thumb will points in the direction of the north pole. So this is called a right hand grip rule. So this was lecture number 2, students. I hope so this will be much more easier for you to understand now. So read this lecture again, understand it, learn it, and make your notes. Thank you so much.